Okay, so welcome back to the last lecture of this finite volume series, and where we will continue our discussion where we left in the last lecture. Now, grid generation, if you recall, you can actually all your realistic complex grid would be in this nature. When you have a complex grid this kind of a nature, either you have option of generating unstructured grid, that is one option, or you can generate a structured grid, then you need to transform this kind of system to a xi eta system or the regular coordinate system. And how you do that? You have this kind of a physical domain, and this is what it transformed to computational domain, and the way it is done, it essentially goes to a uniform xi eta direction, and as it can be xi xy and eta, this would be xy. So, your del x would be xi x del xi plus eta x would be del eta, and similarly del y would be xi y del xi plus eta y del eta. And once you transform them, then you end up getting a Jacobian of transformation. So, this we have actually discussed when we are talking about grid generation and the transformation, or rather talking of the PDEs from there. So, this is how one can do. Now, typical grid generation technique, if it is a structured system, then either one can use some kind of a algebraic grid generation technique which can take care of these different calculations algebraically and then generate the grid, or one can solve for the PDE techniques. PDE means you solve for the partial differential equation and then get the, or elliptical grid generator, that means you solve for some elliptical PDEs. So, these are the different standard available techniques what one can use, and once you, and these days there are a lot of commercial softwares which are available which is dedicated for the grid generation, and as per your requirement of your code you can generate the grid either one of these technique which is adapted, but it is very important to know how those commercial packages actually works. They behind their grid generating software or their graphical user interface, they actually solve either of this kind of technique, whether it is a algebraic fit or partial differential equation kind of thing or elliptic. Now, the same scenario gets changed when you go down to unstructured grid. Here unstructured grid, as we have seen throughout this lecture series, what kind of element it requires. So, one very common approach is that use domain nodalization approach, that means you pick a node, then calculate their distance, and there is a algorithm which is associated with that, or you can do some triangulation kind of approach, and that means you generate some triangular element or do some triangulation and look at the area and then try to generate the grid. So, again your grid generation software, when you try to generate unstructured grid, it does or takes care one of this algorithm and try to do that. So, the details of that, if you are interested, you look at any textbook where which is very much dedicated from the grid generation, and then find out this. But you have to note that you cannot avoid grid generation when you are talking about CFD calculation, because end of the day your CFD calculation needs a grid which will be the representation of your physical domain. Now, moving ahead, most of our practical problems are turbulence in natures, and what happened turbulence in field, that turbulence fields are not like your laminar flow field. So, you have different kind of scales. If you look at your instantaneous flow field which is shown here, which essentially is a like of chaotic in nature. Turbulence, in one word you can say that the chaoticness of the fluid particle. Now, there is a different approaches to model the turbulent flow field. One approach is that you have all sort of small scale which is direct numerical simulation which solve all that details. Details means it means all the scale, or intermediate between DNS And other case you could have Reynolds average Navier-Stokes equation, which can solve. We will see how the Reynolds equations are obtained, solve all the mean quantities, and in between that you have LES which solve for the large structures. So that is how, but theoretically this is how your instantaneous flow field looks like. Now in a LES you actually do some sort of a filtering in physical space, and once you do the filtering, this gets you back the fluctuating component and instantaneous component which is subtracted from the average quantity. Now if you look at the scales, this is at the two different Reynolds number. This is Reynolds number 1 which is smaller, and this is at the double of that. You look at that structures. So this is a macro structure which are look similar, that means this structure we are talking. So they look quite similar in both the situation, but at the high Reynolds number you have large range scale, so increase in the small range microstructure. That means we are talking about this structure, these are the microstructures. And turbulent flow field is kind of is a mixture of this macro and microstructure or built in that. So how the energy goes from 1 to n. So whatever field is there, these structures are called eddies or vorticities, and these eddies are of different sizes. Now that depends what is the maximum characteristics length of a eddy. This is possible or can be defined based on your geometry, because if you have a channel, the characteristics length or which is the maximum possible size of the eddy would be the channel diameter. So what you define, one is length scale L, velocity scale UL, time scale, and the Reynolds number. So turbulent kinetic energy is essentially produced at the macro structure, then it breaks up to the smaller eddies, and then smaller eddy to smaller eddy, and finally it dissipates. So the energy cascading process is like this, from large structure. So this is the large structure or large eddies to go down to the smaller eddies, and smaller eddies from there through viscous dissipation it actually dissipates. So this is the energy cascading process from the large scale to small scale. Now once you say that, what is the primary mechanism? The primary mechanism lies behind this energy cascading process is the vortex stretching mechanism, which is essentially talking about, you think about a closed vortex tube like this which is shown here, and then you have a small vortex which is labeled W1 and which is stretched at this condition, and then this loses. So total velocity which is given is u1 plus u2, and the kinetic energy is estimated at half rho u1 square plus u2 square. So the energy conversion is that small eddies from this large to this gains the energy and this loses the energy. So it is essentially the vortex stretching mechanism, from this to this the energy cascades. So once it happens, the smaller one actually gains the energy and larger one actually loses the energy. So one can think about, it is like a vortex street. So many parallel small vortex tubes like that, and now see flow is invisibly unstable because of the vortex sheet rolls up. Now once that rolls up, it generates a new vortex sheets, and from this process continues, and this generation of smaller and smaller scales. So that is how from larger scale to smaller scale this process repeats, and it generates the different scale of vorticity. Now if you need to scale this energy and the macrostructure rate, so here the picture shows how the large scale eddies are formed. So this is the width of the mixing layer, u is the velocity, then the macrostructure, the length scale would be the characteristics length scale. As one can think, if you have a channel, then this could be the order of the diameter of the channel and the velocity at the inlet. Now the energy of the large scales are order of u naught square, time scale of the large eddy is L naught by u naught, and energy transfer rate is U naught cube by L naught. Now, the viscous dissipation rate at small scale must be of the same order energy transfer rate at the large scale. That is how the energy balance is maintained, and epsilon is can be estimated, which is known as the energy dissipation or kinetic energy dissipation, that can be estimated like this. So, what shows that it could be of this kind of. Now, if you scale down the small scale of the microstructure, then the dynamics of the small scale in turbulence are pretty much dominated by the viscous dissipation. So, your kinematic viscosity and epsilon come into the picture, and the smallest scales are termed as the Kolmogorov scales, because Kolmogorov provided that hypothesis. So, their length scale would be of which we say eta, which is estimated as nu cube by epsilon to the power 1 by 4 u eta, that is the velocity and time scale, and the Reynolds number at the eta scale is eta u eta by nu. So, and the ratio of Kolmogorov scale to the macrostructure, if one has to find out, one can find out this length eta by L naught is R E naught to the power minus 3 by 4, u eta by u naught is R E naught to the power minus 1 by 4, tau eta by tau naught is this. So, increase in the range of scale as with increasing R E. So, if you have a higher Reynolds number case, your scales become smaller, and that is what you need to, essentially your computational grid needs to take care of that small scale. Now, this if you put together in a nicely picture, this is how the energy cascading actually takes place. This is the characteristics length scale, and then you have a energy containing range, or this is your macro structure where all the kinetic energy is produced. Then from there you come, this is called the inertial subrange, where the energy process follows, and you finally get this length scale, and it comes down to the dissipation range. So, the between dissipation and inertial there is a demarcation line, and this is between inertial and energy there is a demarcation line, and these are the microstructure or universal equilibrium structure, and this goes through the dissipation. So, one hand there is a production, energy transfer takes place to the smaller one, and then it goes up. So, that is how from small scale to large scale the energy transfer process takes place. Now, if you scale that, one can scale the inertial range in the like this, and you can characterize these things. Now, Kolmogorov provided this theory that three hypotheses. One is that local isotropic of the microstructure, then the statistics of the microstructure have a universal form. So, that is why the scales in the dissipation range are quickly determined. So, any textbook on turbulence you will find these details. These are nothing new, just to give you an idea how turbulence happens before you. So, how one can actually describe, either it has to be described statistically. The Reynolds proposed some decomposition of the mean flow field, you have an instantaneous flow field. So, you can decompose on the mean and fluctuating component. So, which will actually lead to the Rand's equation or Reynolds average equation. We can see that how it is done, and then you get some turbulence model to close that down. So, this is how your small scales are defined, and this is your instantaneous flow field. So, Reynolds averaging says any flow variable would be one mean and fluctuating component, and if you do time averaging, this is time averaging, this is how you evaluate that. So, this is the Reynolds decomposition. Then you also can do like spatial averaging. So, this is called, it is a different ways one can define the averaging, and then other way one can do ensemble averaging. This is called ensemble averaging. That means you collect the sample multiple times and divide by that, that gives you. There are certain averaging rules for the RANs. One is that if you take the average of the fluctuating component, that is 0. double bar of that same. If you take the delta phi of the average, it is delta phi bar, phi plus phi bar, it is like that. So, these are the certain Reynolds averaging rules which follows this. So, once you try to derive your Rand's equation, so that means you have a flow field which will be average plus fluctuating, pressure is P plus P prime, temperature is T prime time prime, and these are all component. If you put these things back in your continuity momentum equation and energy equation, your continuity equation looks like this. This is your continuity, this is your momentum equation. So, all the variables like pressure, velocity, temperature, again this is what we are writing for incompressible cases, because the density variation is not taken into consideration, and this is my energy equation. And after applying those law, the Reynolds average form of the equation will look like this, which will only solve for the average quantity or rather mean quantity. So, it solve for or mean profiles, and the term which will appear there is a Reynolds stress term in the momentum equation, which is a tensor 3 by 3 matrix, and same thing in the energy flux, which will be a cross term of the u prime t prime, v prime t prime and w prime t prime. Now, one important hypothesis which is used is the Boussinesq hypothesis to close these terms. So, this Reynolds stress term is correlated like turbulent viscosity and molecular viscosity, and your kinetic energy is computed like this, and at the same time your pressure, Reynolds stress is usually combined with the pressure gradient term. So, the turbulent pressure would be like this, and your thermal fluxes are calculated like that. So, this Reynolds stress term is become an quantity which can be correlated with the mu t, and this mu t is the term which is called the turbulent eddy viscosity. So, this turbulent eddy viscosity, now everything boils down to the system. If you look at the system here, it will be a diffusion term which will have some effective viscosity mu plus mu t. That means that this is your effective viscosity in your momentum equation. Similarly, in your thermal equation there will be effective conductivity. Now, how to calculate this? So, that gives rise to a different kind of turbulence model, and if you have mu t, it is estimated like this, and one can have algebraic turbulence model, one can have one equation model, one can have two equation model, and then one can have second order closure model. So, there are different kind of Rand's model one can see. So, if you look at the complete picture of the Rand's equations, so there will be continuity equation, momentum equation, energy equation. Now, this is kinetic energy equation, which you can see there is a effective viscosity, epsilon equation which is Ka equation, kinetic energy, epsilon equation, and turbulent frequency omega. So, these are the set of equations, and once you discretize them in your finite volume, this is exactly what you get for the, this is for turbulent kinetic energy. So, again the equation looks same. Here the coefficients for kinetic energy would be mu effective EF by this is the AC, then time transient term. So, these are all coefficients which you get for the K equation. Now, similarly one will get an equation for epsilon. This is epsilon equation, and accordingly your coefficients will be modified as per the epsilon equation. This is your AF, AC previous time step, and B source term. So, this will retain all the, or one can think about the omega equation too. So, all these equations will appear there. Now, one important thing it will happen is that calculation of the wall function, because all these turbulent equations these are having used, and that time, and the thing is that near the wall flow field resolution is very important if you have a domination of the viscosity. So, to resolve that, one has to, typically there are 3 different layers where the layers can be divided. One is called the viscous sublayer, and where your distance or the your normal distance is defined d plus less than 5, then your buffer layer where d plus lies between 30 to 5, and then inertial sublayer. So, where d plus lies between 200 to 30, and d plus is estimated like that, d perpendicular distance by u tau by nu, which is y plus, and u tau is nothing but tau at the wall by density, and d is the normal distance to the wall. So, that is how you can calculate. Now, if you go to, so viscous sublayer, then this is how u plus and y plus they are connected, and if you have a moving wall, then u plus is connected like that, viscous sublayer, and for k and epsilon typically this is what done, k or omega. So, for 2 equation models this is how it is done. Now, one can see when it comes down to a boundary element, this is a boundary element, and I mean where close to the wall, and you have to boundary element at wall, because the normal calculation needs to be done. So, one can calculate the normal distance dc plus like dc u tau by nu and kinetic energy like that. So, which will get you back dc like c mu kc and c mu kc. So, as long as dc perpendicular less than d limiting plus, the point lies in the viscous sublayer, otherwise it will be in the inertial sublayer. Similarly, this is the turbulence production term, and this is the dissipation term which can be estimated at that cell, and this is the turbulent frequency term, and one can estimate the wall shear stress also. So, once you estimate all these, I mean these are the calculation for that, and one can actually get all these calculation for at wall, these information can be calculated. Now, the other way one can think about using some sort of an improved wall function, because what happens that sometimes the grid resolution is not sufficient. So, one may use the improved wall function, and you can actually derive these equations for improved wall function. Or thirdly, one can think about some scalable wall function. Essentially what you do, you need to calculate the normal distance, and once you calculate the normal distance to the wall, then you can solve for it. Now, how do you calculate the normal distance? That is the critical part. Let us see a 2-dimensional control volume or 2-dimensional control volume. How do you calculate the normal distance? So, the normal distance can be calculated is just using some sort of an based on solving a differential equation. So, this can be calculated by solving a differential equation, and which could be solving a like an Poisson, Econal or Hamilton-Jacobi kind of equation. So, if you look at the Poisson equation, del 2 phi equals to -1, then which will be boundary condition, it is on wall, and del phi dot n equals to 0 elsewhere. So, the normal distance can be calculated equals to minus del phi magnitude of that plus del phi square plus 2 phi, which is minus square root of del phi by del x plus, square plus del phi by del y square plus del phi by del z square plus square root of del phi by del x square, del phi by del y square and del phi by del z square plus 2 phi. So, and if you solve the turbulent flow problem and use everything in the in your governing equations, you get this geometric diffusion coefficient. Geometric diffusion coefficients at the face is EF by dCF, and your discretized equation would get modified like AC phi C plus face NBC AF phi F equals to BC. Here AF equals to minus G F, which we got here, then AC equals to minus summation over F GF, and BC equals to VC plus F, which is del phi F dot TF. So, that is how you can calculate the normal distance. So, essentially that talks about how you implement all these things in your system of equation, and if you that also brings down to some extent the closure of these lectures, and what we have actually talked our numerical scheme based on finite volume method, and then we talked about the classifications of the PDEs and all these things. Initially, for the finite volume method, the prime objective of any CFD is that you have a physical problem. So, that transform to a discretized equation, applying this finite discretized equation which is nothing but a linear system f e equals to b, then apply a linear solver which actually get you a solution, and that solution should be representing to physical problem. So, the global picture what we started off, if you close it down, you have a physical problem of interest in hand, you apply your numerical technique, the one which we have discussed here is the finite volume, you get a discretized equation that is essentially leading to a linear system, and then we discussed all different kind of linear solver like iterative solver, direct solver, and which will get you the solution. Now, the physical problem which is governed by these PDEs, they are actually, then the PDEs are essentially we talked about all different kind of discussion where diffusion separately, convection separately, transient separately, and we have taken care of everything together when we combined everything back to the Navier-Stokes equation for fluid flow solver. And when you go down to the fluid flow solver, we have actually used our incompressible solver, then we talked about the pressure velocity coupling and the interpolation, then finally talking about simple and simple family based algorithm. Then we moved to the compressible, where again we discussed about the discretization and boundary condition, and finally we touched upon the grid generation and the turbulence modeling, and that concludes the discussion on finite volume, and I hope it will be helpful to get started with finite volume method. Thank you.